Okay. So first, so a few talks ago, I have already talked about these algorithm, the breadth first search method. So today I'm going to talk about it a bit more deeply, a bit, and I'm going also to show, yes, a more detailed, and I'm gonna explain the code, the source code, the pseudocode for breadth first search. Okay, now let's start with the breadth first search with the time complexity of breadth first search. So I have already talked about this. So I said it before. So it runs in a time complexity of big O notation, O of V plus E, V plus E. So V here represents the vertices and E represents the edges. E represents the edges. So in other words, V plus E is just branches in this tree, in this binary tree, or in some tree or some
graph.
Yes, in some graph. Yes, in some a cyclic graph, directed acyclic graph, for example. The branches plus the total amounts of nodes. Okay, so also an important note to make is that the breadth first search can be used as a building block in a lot of real world applications in many algorithms. So it differs from depth first search, the other search on graphs or trees, in the way that it explores the graph, in a way it traverses the graph. In
traverse is a good word.
Yeah, okay, so it traverses the graph. Okay, so the main utility or the main usage of breadth first search is particularly one thing. So that is its main utility. That is the finding the shortest path on an unweighted array, on an unweighted graph, for example. Breadth first search. That is the first slide. The first slide. So the let's look at the way it explores or traverses the graph. So it starts at the node, for example, at the first slide, from the zero node. By the way, can you see this slide?
I
can. Okay.
I can. Well, I have it here. I have it on my screen.
Okay. Okay. So we're starting at the, for example, zero node or at some root node, and before moving on to next nodes, it first looks at all of the node variables. So it now first it explores the in layers. So first it explores all the nodes in yellow. It's visiting all the neighbors, and then it visits all the neighbors of these nodes, of yellow nodes, nodes in yellow, and so on. So it continues to look through every node in some laid fashion or some laid manner.
Order.
Yes, in laid order, or so in other words, level by level. We'll also use a queue data structure when we're going to look at the pseudocode. The queue, it's important to maintain the queue for node visits. Okay, now let's look at some pseudocode for breadth first search. Okay, so first, that is the next slide, the second slide. We'll need two variables. N, that is the number of nodes in the graph, and J variable, that is the adjacency list. So this adjacency list represents the
adjacency. Did you say?
Yes, adjacency. Adjacency list. Okay, that adjacency list represents our unweighted graph. So it represents the graph we're looking at. we're searching at.
Okay.
Okay. The next is the function. This function, breadth first search, takes two arguments: the start node, the s node, and the end node. So we want to find the shortest way, the shortest path from S to E. Okay, so let's divide this function in two parts for simplicity, into solve method and reconstruct path method. So solve method will execute the breadth first search on our graph, and reconstruct path will so by the way, it will reconstruct path after we have done the breadth first search. Okay, so
What do you mean reconstruct the path?
Yes.
What do you mean? What do you mean?
So
reconstruct the path.
So as we have looked through the array, through the graph, the main utility for this is we want to find the shortest way. So as we look through the graph, we now know how to say. We know all of the where the nodes in the array are on the graph are, and
Okay, I know what you mean now. Okay, so not reconstruct, but construct the path.
Okay.
Not reconstruct. Yeah, okay. When you say reconstruct, I mean when you put in front of a verb, it means again. So I thought, did he do it before? Okay, so you just want construct the graph, right? Without
okay.
Without re.
Okay,
Does
construct.
It make sense?
Yes, it makes sense. Okay, construct the path. Okay. Okay, now first, let's take a look at the solve method. That is the third slide. So here we are inside the solve method. So first thing we do is we're initializing the array or the queue data structure. We're initializing the queue data structure. So we want for this structure to so we can enqueue the elements into the structure and dequeue. Okay, so we'll need the add starting node to this queue. And next, so we're enqueuing the starting node, the s node, into this queue. And next, we want to declare the visited array, the Boolean array with all false values. This array would have the size of n or the length of n, and it tracks whether or not we have visited this node or not. Okay, so by the way, that corresponds to gray and yellow nodes in the first slide. Okay.
Okay, got it.
Okay, so the last thing we'll need is the prev array. So this array, the prev array, on the slide, the prev.
With the prep, P-R-E-P?
P-R-E-V.
Oh, prev.
Oh, okay, prev. Okay.
Yeah, like previous.
Okay.
So it's short. Previous.
Okay.
Okay, no, it's okay. No, it's just that prev.
Okay, prev. So this prev array will help us track who is the parent of the node for further path construction. Okay, so now let's loop while Q is not empty. We're pulling out the top node from the queue. As we see, we're pulling out the top node from the queue, and now we're getting all of the neighbors. We're reaching inside the adjacency list, the adjacency list, and we're getting all of the neighbors of this node that we're looking at, that we have pulled out of the queue. We have. Okay. So.
I see. Yes.
Okay. So next we're looping over all unvisited nodes. So once we find a next unvisited node, and here we're enqueuing the next. We're enqueuing this next.
We're dequeuing.
Oh,
Dequeuing.
no, we're
NQ.
enqueuing.
In other words, you're putting it in the queue.
Yes, we're putting it into the queue. We're enqueuing this next variable, so which represents the neighbor of this node. Okay. So we're once we found, we're enqueuing these unvisited neighbors and marking this node as the visited. We're adding it, so we marking it as visited in the visited array. Okay.
Sure.
Okay. So once the queue is empty, while this queue is empty, we're just returning the prev array. So our breadth first search is complete. We're just returning the prev array. Okay.
Yeah.
Now let's look at the next. Okay, back inside the breadth first search method. That is the fourth slide. Back inside the breadth first search method, we're taking the output from the solve method, which we have. So we declared the prev array, and that is the result from the solve method. We put it into the prev array, and we're putting this prev array into the construct or reconstruct path method. Okay, so we're calling the reconstruct path method with as the start and end nodes and the prev array. Okay, now the next slide. We're starting to construct or reconstruct the path backwards from E. We're declaring an array path, the empty array path, and we're looking backwards. We're looping backwards from the end node to the from the end node all way back the start node. We're making all way back to the start node. So the reason why we had to initialize the prev array at all. Initialize. Okay, initialize. We had to initialize prev array at all null values. Is that because now we are checking whether or not the loop has stopped. Okay, the loop should stop. And next, once we have looped all of the elements from backwards from E to from end to start, we have to return our path. So that is so because we have looked from the end to start. So from this so to this path start from start and not from the end node, we have to reverse it, and then the important note is that we need to okay, last but not least, we actually have to make sure if this path exists. So it might not be possible to go from node S to node E. For example, if the graph is disjoint. So if this is the case, we're just returning the empty array. Okay. So we're returning the empty array if E is unreachable from S point. And in other situation, if we can go from path from node S to node E, we're returning the path. Okay, so now we have looked through the breadth first search method, a bit deeper about how it works. So it works in a laid fashion, and we also have looked through the breadth first search pseudocode. So now pseudocode. So that is the end of my talk. I'll wrap up here.
Okay, all right. Okay. That's a good talk. Listen, what do you think? I mean, I have to think about this. Is it clear what it does to you, or no?
Well, yes, in some, yes, yes. Well,
In some ways. Yeah, I'm thinking about this. Okay, yeah, there's a lot of things happening in this in this search. So,
okay.
yeah,
Well,
interesting though. Okay,
okay. Well, in general,
been a while.
the algorithm is understandable.
Complicated. Yeah.
Well,
Okay.
so it is a bit complicated, but yes, it is understandable.
Understand. Okay. Okay.
Yes.
Yeah, interesting. Okay.
Okay.
All right.
So,
Well,
uh,
very good. Yeah.
okay, thank you. So I'm going to now look for another videos from this author. So that is
Okay.
I
Okay.
relied on the video of the teacher you sent.
Okay.
Well,
Okay.
he has
Okay.
a lot of not a lot of other talks to talk about, and a lot of other
Okay.
algorithms to talk about. Um,
Okay.
okay. So well. So
So
thank.
yeah, but if you need more material, I could look, but I think you have enough for now.
Well, thank you, Robert. I have yes
Sure. Yeah.
the
Okay.
uh,
Have a
the
good birthday.
thank
Have
you,
fun
thank you very
tomorrow.
much.
All right.
uh, oh,
Take care.
okay. Thank you, Robert, and goodbye.
Sure. Bye bye.
Goodbye. I will now call my dad.